Have you ever stopped to wonder what the fundamental building blocks of our universe actually look like? It's a question that some of the greatest minds in history have obsessed over. Well, today we're going on a journey to see how our picture of the atom has been drawn, completely erased, and then redrawn over and over again. So really, what does an atom look like? I mean, you've seen those classic diagrams in textbooks, right? With the little balls orbiting a center. Well, the real story is so much weirder and more interesting than that simple picture. Think of it like a detective story, full of clues and shocking twists that changed everything we thought we knew. Here's our roadmap for this little adventure. We're going to jump in our time machine, starting way back in 1806 with a simple, solid ball, and we'll end up in the bizarre and fascinating world of quantum mechanics. Each one of these steps wasn't just a small change, it was a revolution in how we see reality itself. Okay, let's rewind. Our story kicks off in the early 1800s. We meet this guy, John Dalton, who laid the entire groundwork for modern chemistry with an idea that was revolutionary and honestly beautiful in its simplicity. So Dalton proposed that everything, and I mean everything, is made up of these tiny, solid, unbreakable particles called atoms. The best way to picture it? Think of them as microscopic billiard balls. They're fundamental, you can't destroy them, you can't divide them. This was the first truly scientific model of the atom, and it was an absolute game changer. Dalton's whole theory was built on a few core rules. He said, first, all atoms of a specific element, let's say gold, are completely identical. Second, they combine in simple, predictable ways to make all the stuff around us. And third, in a chemical reaction, they're just getting rearranged, kind of like Lego bricks. You're not creating or destroying them. This idea was the bedrock of chemistry for nearly a century. But of course, science never stands still. At the turn of the 20th century, a physicist named J.J. Thomson comes along and makes a discovery that completely cracks Dalton's perfect little billiard ball wide open. Turns out there was something even smaller hiding inside. And you really can't overstate what a massive shift this was. Suddenly, the atom was no longer indivisible. Thomson had found the electron, this incredibly tiny negatively charged particle. For the very first time, we knew that atoms had internal parts. The simple sphere just got a whole lot more complicated. So, if the atom has these negative bits inside, where are they? And more importantly, where's the positive charge to balance it all out? To explain this, Thomson came up with a rather delicious-sounding analogy. He imagined the atom as a big ball of positively charged pudding, and scattered all throughout this pudding were the negatively charged electrons, kind of like plums or raisins. The whole thing was electrically neutral, and for a while, this plum pudding model was the accepted picture. It made a lot of sense. But you probably know where this is going. The story was far from over. A former student of Thomson's, a brilliant guy named Ernest Rutherford, decided to put this whole plum pudding idea to the test. And what he found didn't just challenge the model, it completely obliterated it and changed physics forever. So Rutherford's team set up this experiment where they fired tiny, positive particles at a sheet of gold foil that was unbelievably thin. Now, they expected those particles to just zip right through the soft pudding, and most of them did. But some of them bounced almost straight back. Rutherford famously said it was as incredible as if you'd fired a cannonball at a piece of tissue paper and it came back and hit you. It just shouldn't have happened. This bizarre result led to a truly mind-bending conclusion. The reason most of the particles went straight through was because the atom is almost entirely empty space. The few that bounced back must have hit something incredibly small, incredibly dense, and positively charged. And just like that, the nuclear model was born. All the positive charge and pretty much all the mass of the atom were packed into this impossibly tiny center called the nucleus. And the electrons, they weren't in a pudding. They were just out there, somewhere in that huge, vast, empty space that makes up the rest of the atom. But there was a huge problem with Rutherford's model. A fatal flaw, really. It was completely unstable. So another scientist, Niels Bohr, came along to solve this puzzle and bring a new kind of order to this chaotic atomic world. So here was the big question. If opposites attract, why on earth don't the negative electrons just spiral straight into the positive nucleus? According to all the laws of physics at the time, the atom should collapse on itself in a fraction of a second. But obviously they don't. We're all still here. So why not? To solve this mystery, Bohr looked to the heavens for inspiration and proposed a new, beautifully elegant analogy. Bohr suggested that electrons weren't free to just roam wherever they wanted. Instead, they were locked into specific energy levels, or orbits, kind of like planets orbiting the sun at fixed distances. They could jump from one orbit to another, but they could never, ever exist in the space in between. And this simple rule perfectly explained why atoms didn't just collapse. Now, Bohr's planetary model was a masterpiece. It was neat, tidy, like a tiny solar system, but it was also the last great model of its kind. Because at the exact same time, a revolution was brewing in physics, a strange new world called quantum mechanics, and the atom was about to get a whole lot weirder. So, is the atom really a tiny solar system? Well, this new quantum way of thinking said, absolutely not. New experiments started to show that electrons don't behave like predictable little planets in fixed paths. Their reality is much fuzzier. And this brings us to the modern concept of an orbital. Scientists had to completely ditch the idea of a fixed path. An orbital is not a path. It's a region of space where an electron has a high probability of being found. We can't know exactly where it is and where it's going. We can only know where it's likely to be. This gives us our current best picture, the electron cloud model, brought to us by pioneers like Erwin Schrödinger. In this view, electrons aren't even really little balls anymore. They act more like waves of probability. The denser parts of this cloud are just the areas where you're most likely to find the electron at any given moment. It's not a simple picture, but it's the one that actually fits the bizarre rules of the quantum world. So let's just quickly recap this incredible story. We started with Dalton's simple, solid billiard ball. Then Thomson found the first clue hidden inside, the electron, giving us the plum pudding. Rutherford's bombshell experiment revealed the tiny nucleus and all that empty space. Bohr tried to bring order with his neat planetary model, before Schrödinger and others embraced quantum uncertainty, leaving us with today's probability cloud. You see, each model wasn't wrong, just incomplete. Each one was a stepping stone showing us exactly how science is supposed to work. And that's our journey. Our picture of this fundamental particle has been completely revolutionized time and again over the last 2 centuries. Which leaves us with one last, really fascinating thought. What are we missing now? What new discovery is waiting just around the corner to completely redraw our picture of the atom one more time?